Assalamu alaikum. We know when the frequency of a vibrating object matches with the frequency of another vibrating or oscillating object, resonance takes place. In this video, we'll discuss the resonance in series RLC circuit. Now, before going ahead, let me tell you what is a series RLC circuit. An RLC circuit is obtained by connecting a resistor of resistance R to an inductor of inductance L with a capacitor of capacitance C together in a series. Now, when components are connected side by side, we call such combination as series combination. So here, resistor, inductor and capacitor are connected in series. Then, to this we apply the AC voltage with the help of this AC source. Now, this RLC circuit is connected to an AC source. When the frequency of this AC source, this applied AC source, matches or becomes equal to the frequency of RLC circuit, resonance takes place. I repeat, when the frequency of applied AC source becomes equal to the natural frequency of series RLC circuit, resonance takes place in the circuit. Okay, so let me write this one here. The angular frequency is a representative omega R. Here R represents a resonance. So we can call this one as angular resonance frequency. And when it becomes equal to the natural frequency of RLC circuit. Natural frequency of RLC circuit is 1 upon root of LC. This term represents natural frequency of RLC circuit, and omega R represents the angular frequency of applied AC source. Now, we know here omega R can be related with angular frequency, can be related with the frequency as a 2 pi f. Here I have used R, so here also I use R. So this is the frequency and this one is the angular frequency. If I use this in the above equation, what I will get? I get this. Substituting this value in the above equation, we get 2 pi of R is going to be equal to 1 upon root of LC. Now, from this expression, Fr from here, Fr value is going to be 1 upon, here 2 pi is taken to the right hand side. Here it multiplies, here it will divide. 2 pi root of LC. This is what we obtain. Okay. This represents angular frequency and this represents frequency. So I take the resonant condition now. This equation I write here. Omega R 1 upon root of LC. Now, I square both sides. What I do? I square both sides. So, omega R will become omega R square. Similarly, square of 1 is 1. It's kept as such. Now, square of root of LC on squaring become LC. Correct? Now, I'm going to make a certain changes to this. Look at this carefully. What are the changes I'm going to make to this? Now, here instead of omega r square, I write omega r multiplied with omega r. And it will be equal to 1 upon LSC. Now, I keep 1 omega r here as such, and another omega r is taken to the another side of the equation. So, I'll get this. Omega r comes equal to 1 upon omega r multiplied with LSC. This is what I obtain. Now, I'll make a certain changes to this. Now, I keep omega r multiplied with c here in the denominator, and L is taken to the left hand side. So, from this equation, omega r, when L is taken this side, it will multiply. Now, down what we'll have? We have only this. Omega r c. Now, we know very well the product of angular frequency and inductance of the inductor provides us inductive reactance XL. What is this? It is nothing but XL. In similar way, this is 1 upon omega c. It gives us capacitive reactance, that is XC. Now, alas, we have obtained this expression that shows that inductive reactance is equal to capacitive reactance at a resonance condition. Clear? When the angular frequency of applied voltage matches with the natural frequency of RLC circuit, in that condition, or in that case, inductive reactance becomes equal to capacitive reactance. This is the condition for resonance. No? This is what happened in the resonance condition in RLC circuit. Clear? Now, what do we understand from this? When XL becomes equal to XC, the current in the circuit becomes maximum, and the total impedance reduces. Now, we'll find out that. Here I write the effects of series resonance. Effects of series resonance. As I told you earlier, at a resonance, the current in the circuit increases. Now, with a reduction in the overall impedance of the circuit. Okay. We know in RLC circuit, impedance. What is impedance? Impedance is nothing but the total resistance offered to the flow of current by the circuit. Okay. And it is represented by letter Z. Z stands for impedance, and it is nothing but root of R square plus XL minus XC whole square. This is the expression which represents the impedance offered to the flow of current by this RLC circuit. So here, if I apply resonance condition, at the resonance, XL becomes equal to XC. If it is so, what I do, in the place of XL, I write a XC. We'll see what happens if I do so. I take this equation, root of R square plus, what I do, I'm going to apply this condition here in the above equation. So in the place of XL, I'll write XC. So XC. minus XC. I square it. Okay. Now when XC is subtracted from SC, what do we obtain is ultimate? 0. So it becomes 0. So Z will become equal to root of R square plus 0. And this is found to be equal to Z root of R square. When we take a root of R square, we obtain this expression. Z becomes equal to R. It means the impedance of this RLC circuit becomes equal to resistance. Okay, it means at a resonance, the opposition to the flow of current by the circuit has reduced to R. Clear? So when this happens, automatic, the current in the circuit will increase. We know whenever resistance in a circuit decreases, the current will increase according to Ohm's law. Okay. Therefore, the current in the circuit becomes maximum, and that maximum current in the circuit becomes maximum, and it is represented by letter IM. Okay, here the value of IM, maximum current, is obtained. Now we know Ohm's law, V equals to IR. This is Ohm's law. From this, I equals to V upon R. Similarly, IM will be obtained if we divide voltage with the resistance. In our case, it is impedance. Right? So maximum or peak voltage is taken as Vm and divided by impedance. What is that? R square plus XL minus XC whole square. Oh, this is the thing. Okay. But in our case, at the resonance, this can be written as Vm upon Z. Clear? No, the value of this one is nothing but Z. At resonance, what happened? Z becomes equal to R. So IM becomes equal to Vm upon R. Okay. This clearly shows that the current in the RLC circuit becomes maximum at a resonance. Okay. Now this can be shown with the help of a simple graph drawn by taking current along the y-axis and the frequency along the x-axis. Now I draw a graph here. I take a current along y-axis and a frequency. Frequency meter f along the x-axis. Now, suppose I say that this is the resonant frequency. And at a resonant frequency, so this is the resonant frequency. At resonant frequency, the resonance takes place and the impedance value reduces and the current becomes the maximum. See, it's here. I get one curve here. This curve shows that R value is here. R value is less. When R value is less, we obtain a current now shown by this peak. Now I'm sorry, yeah, this represents some R value. Here R value is taken as maximum. When the R value reduces, I'll get another peak. The peak obtained appears something like this. This is the peak I obtained. Here, this edge provides me the maximum current. This provides me the maximum current, represent letter IEM. Okay, and here we'll obtain this kind of curve, this peak, this maximum curve, by reducing the value of R. And here reduction the value of R takes place at a resonance. Okay, so at resonance I have drawn two different curves, two peaks. One provides a maximum current by reducing the value of R, that is by reducing the resistance of the circuit. When the resistance offered to the flow of current by the circuit is more, is maximum, there you can see the value of I is less. Clear? So this is what happens when the resonance takes place in the circuit. Now, what are the different applications of this resonating RLC circuit? That we will discuss in the next video. I hope the video is useful. If you have any kind of doubt related to the topic, can you put a question in the comment section? Thanks for watching.